So we've looked at vector arithmetic and dot product and cross products. So now we can take it a step further and take a look at matrix arithmetic. So first, let's take a look at scalar multiplying a matrix. A scalar, remember, is just a number like 5 or 2, like we have here. And a matrix is a set of vectors, right? So in this case, we have 6, 2, -3 in row 1, and then 1, 0, 4 in row 2. So when you take a scalar and you multiply it by a matrix, you get a matrix of the same size, right? So matrix C is the exact same size as matrix A. And the way you make this, you complete this multiplication is you take that scalar and you multiply each individual cell in the original matrix and you place the products in each of those same locations. So little a scalar is 5. 5 times 6 is 30, so you place it right there. 5 times 2 is 10, so you place it right there. 5 times -3 is -15. 5 times 1 is 5. 5 times 0 is 0. 5 times 4 is 20. And another example here, scalar 2, b equals 2 times the matrix B. So 2 times -1, 2, and so forth, right? When you add or subtract matrices from each other, both matrices must be of the exact same size. So both matrix A and B have 2 rows and 3 columns. So this can work. If it's not the exact same size, you cannot add or subtract them from each other. It doesn't make conceptual sense either why you would want to do that. So sometimes if you really want to do it, you might need to fill in a set of 0 vector vertical column or horizontal rows just to make them of equal size for a specific reason. But in this case, they are of the same size. When you add or subtract matrices, you take each cell and you match them directly. So in this case, A plus B, you take column 1, row 1, you go 6 minus 1, gives you 5. Column 2, row 1, 2 plus 1 gives you 3. Column 3, row 1, -3 plus 5 gives you 2. Column 1, row 2, 1 plus 2 gives you 3, and so forth. And then when you subtract matrices, A minus B, it's the same thing. You subtract them, right? 6 minus -1 gives you 6 plus 1 gives you 7. 0 minus 3 down here gives you -3, and so forth. Sometimes you'll have matrices of the same physical properties, but it's swapped, right? The columns represent something, the rows represent something, and for whatever reason you have another matrix and you define them in opposite form and you want to directly compare them. So what you can do in that case is something called transposing the matrix. And one of the notations we use is we put a superscript T above the matrix symbol. And so what happens is your column value and your row values switch, right? So 6 is in column 1, row 1. So when we transpose the matrix A, we put it in row 1, column 1. So same location. Look at this 0 value. The 0 value is in column 2, row 2. So we put it in column 2, row 2. Same actual location. But what about this one? -3. -3 is in column 3, row 1. So we're going to put it in column 1, row 3. Column 1, row 3. That's where this goes. The number 4, this is in column 3, row 2. So we're going to put it in column 2 and in row 3. So row 3, column 2. And we do the same thing for the B matrix. So we'll see when we can apply this when our matrices are not of the correct size to complete the operation that we're looking for. We can multiply a vector and a matrix, and we'll see in a second after we do this one that we can also multiply a matrix by a matrix. But there are specific rules of the size of the vector or matrix that need to be true in order for this operation to be completed. So I have 2 row vectors as an example, and 2 column vectors as an example, and then we use the same A and B matrix to take a look at this vector multiplication with a matrix. So as an example, let's create a new matrix where we multiply a row vector by this matrix. Okay, so we have 5, 2 multiplied by the A matrix here. And so the operation that we take is we take 5 multiplied by 6, and we take 2 and multiply by 1, and then we add them together. So we're essentially taking the dot product of those 2 vector components. So we're breaking this down into individual dot products. So here we're taking 5 multiplied by 2, 2 times 0, add those together. For this cell here, we go 5 times -3, 2 times 4. Goes right there. And so this is our final form right here. So it's really important that we have certain size requirements. So the vector, or in general form, the matrix that comes first, that number of columns must match the number of rows of the second matrix or vector, right? So how many columns I have here? I have 1, 2. How many rows do I have here? 1, 2. And it's essential because I do the dot products in this way. I take the row and I take the dot product of that row to each of the columns. That's essentially what we're doing here. Why would I do this? What are the physical representations that a vector multiplying a matrix would even create? So, I mean, this is arbitrary numbers, but let's say you were playing a game and you have a bucket and you have so many red balls and blue balls in your bucket. And after every game, there's a chance for you to gain and lose balls in some fashion. Okay, so the vector might dictate the point value of the 2 balls, the red and blue balls, and the matrix itself might represent, for the columns, the games or the rounds that you play, and each row represents the number of blue or red balls that you gained or lost, right? So the matrix or vector C, that's the product of matrix, the vector A multiplied by matrix A, is the total number of points that you gained in each of the individual games. So from game 1, the points in game 2, and points in game 3. So that's one possible reason that you would apply something like this. So you could do this by hand. A vector multiplied by a matrix, or a matrix multiplied by a matrix, basically consolidates many equations that use the same pattern. So that's the effectiveness. It keeps it all concise. And if you start using computers to solve things, you can build in these matrices and vectors, and you can ask it to solve it all at once, right? But understanding the fundamentals of what you're actually asking it to do is really important. So just because we have calculators doesn't mean that we don't need to know how to solve arithmetic. Similarly, just because we have computers to solve matrix vector calculations doesn't mean we shouldn't understand the basics of what we're asking it to do. So here, just another example, right? We take our B vector multiplied by our B matrix. So it's worth the time, if this is the first time you're seeing this, to work this out by hand, or pause the video and just look at all the details to make sure it makes sense what the operation is, right? So these are like dot products between this vector and each of these column vectors. That's what's produced in this final vector or matrix form. Now, if you swap it, you want to make the matrix multiply by the vector, you'll find that because of this rule, you can't multiply a matrix to the a vector by you can't swap these around, right? So But I can multiply the A matrix and the C vector, because the number of columns in my A matrix is 3, and in my C vector, we have 3 rows, so it matches up. Remember, it's the rows and the dot product of the rows, the first set of rows and the second set of columns. So first set rows, second set columns, first set row and second set columns. So 6 to -3 dot product with -1, 1, 4. We go 6 times -1, -6, 2 times 1, 2, -3 times 4, -12. And because it's dot product, we just add them all together. We get each cell becomes the scalar that is the result of the dot product. And then we can do it again for the B matrix and the D vector because they're the correct size. So give it a try. Pause the video, look at the result of these matrix vector multiplication, and make sure it makes sense. Another common reason why we do some matrix vector multiplication is if you're trying to solve for unknowns. So let's say you have these 3 sets of equations and you're trying to solve for x, y, and z. So you can build in a matrix that essentially is your coefficients to your equation, and your unknown variables is a vector here, equating into the coefficient or the constants of your equations over here, right? So why does this work? Remember, it's row times column. So let's say I look at this first equation. This row dot product with this column will be 3 times x plus 4 times y plus -2 times z is equal to 7. And that's essentially what this equation is here. And then, the second row dot product with this vector equals 9 would be the second equation right here. So you can see how it makes it very compact. And in a future video, we'll talk about inverting a matrix, and that's the way that we get computers to solve these types of problems for us. So next, let's take a look at matrix multiplied by another matrix. It's very similar to what we looked at here with a vector multiplying a matrix, except both of them will have multiple rows and columns. So here we have our matrix A and B, and we have the transpose of matrix A and B. Now remember that we are required, when we multiply vectors or matrices, that the first matrix the number of columns of the first matrix must match the number of rows in the second matrix. So because of that, matrix A multiplied by B will give us an error, right? We can't do a dot product of 3 values and the second vector have only 2 values. We don't know what to do with this -3 and an empty set here, right? So we can, but we can take the A matrix and multiply it by the transpose of the B vector, which we have here, right? So when I transpose this matrix, now I have a row with 3 terms, and my transpose B matrix has a column with 3 terms, right? So I have 3 rows here and 3 columns here, and so I need to match my columns and rows. The first matrix columns to match the number of the second matrix's rows, which it does here. And so just like what we saw earlier, right? This dot product, which cell would that be? That'd be right here, right? So second row, second column, second row, second column. So 1 times 2, 2, 0 times 3, 0, 4 times 2, 8. So the dot product of those 2 vectors gives us this value. Dot product of 6 to -3 and -1, 1, 5. First row, first column would give us this cell. Would give us -19, and so forth. Now it's important to note, if you add matrix A, if you say matrix A plus matrix B, that would be equal to matrix B plus matrix A. That you can swap them and it's not going to make a difference. But because matrices are dot products and it's the first row dot products with the first column type of thing, when you swap them like you do here, right? If I say transpose of B times matrix A, you're not going to get the same solution. In fact, you're not even getting the same size unless they're square. You're not going to get the same size, right? So here I have my transpose B matrix and my A matrix, and same thing, right? It's just the dot products. So 1, 3, choose 0 gives me 1 times choose 2 plus 3 times 0, 0. That's these cells right here. So now we know how to multiply a matrix with a scalar, multiply a matrix with a vector, and now multiply a matrix with another matrix. We also know how to add and subtract matrices. So we can start building the toolbox of how to utilize different properties of matrices to manipulate them to solve equations all at the same time. So that's a real power of building matrices. It contains a lot of information, and then you can solve a lot of things all at one time very quickly.